is that better, whatever. Today, okay, really close. I was stuck going back up to my home yesterday evening and was again in big trouble this morning. Nothing bad happened, but I've been hacking ice for 4 hours this morning. So if I look out the deer in the headlights, that's why. Anyway, I'm very glad you're here. I'm kind of not so happy with the issue. I think I should have canceled classes today. I've heard a lot of accidents that happened. So I think they're on I'm just glad everybody's here. But sometimes it wasn't so much snow, but it was very tricky, I think. So related to this, this class is my first priority. You can believe me. I am going to try to have this graded today, but it might not show up on the web until sometime on Monday. So bear with me for that. Also, I know I have to update the PDF notes for the class. And because I have to go and hack some more ice off the road this afternoon where I live, I will have to do that on Monday morning. So you will see the class notes for section E on Monday. Yes?
Can we turn in the pre-test at the end of class, or can we turn it in now?
You can turn it at the end of class. Yeah, sure. All right, that's that. So, anyway, you're all having bunch. That's good to do. So we're looking at microscopy. And when you think about microscopy, we have to keep in mind that seeing is believing. I think seeing is believing. And we want to see in the microscope, but we have to be sure that these are real things. So we have to be aware that sometimes we look at items that are stained, items that are not alive, and in some cases we might be introducing artifacts in our systems. So keep that in mind. Also, for the light microscope, there's definitely a limitation with respect to the resolution, which is at 200 nanometers, and that means organelles and most bacteria cannot be seen in the light microscope. So if we need to look at smaller structures, what option do we have? Well, we have the electron microscope. There are two main kinds, called the TEM for transmission electron microscope and the SEM for scanning electron microscope. So why is the electron microscope better when it comes to resolution? This is because instead of photons, we use electrons, and the electrons, they are put in an electric field to give them an acceleration, a high speed. And electrons, just like photons, can be viewed as having, I'm going to put the volume a little down, as having both a particle character and a wave character. And at low speeds, the particle character of the electron dominates. But at higher speeds, when we get to, I don't know, maybe 10%, a couple of percent of the speed of light, I don't know exactly which speeds are reached in these electron microscopes, the electrons start to behave as waves. And since they behave as waves, with very short wavelengths, we can use magnetic lenses in order to bend and focus these electrons. And so using electrons, we can have very high quality lenses, which is the important good thing about the electron microscope. And because the wavelength of the electron is related to the amount of energy you put in, we can put in a high amount of energy, we get a very short wavelength, such that effectively the limitation for resolution of the electron microscope is atomic levels. So theoretically, and even in practice, you can see individual atoms in the electron microscope. So people have visualized things like heavy metals and gold, individual atoms. So you get really a very, very low resolution, nanometers and less. Now, what is, however, an issue with biological samples is that the samples always will have to be stained. And we'll get to the why. It all has to do with the idea that the way electrons interact with the specimen, it is by collision with other electrons. And since most atoms in living organisms are atoms of low atomic number, they also have a few electrons around them. So carbon dominates the organic molecules, and carbon has 6 electrons. Therefore, there's a low probability for an electron that forms our image to interact with anything in the specimen. In order to increase that contrast, we must add atoms that have more electrons. And there's no other choice, we have to go to high atomic number electrons, which are the heavy metals. So typically, samples in the EM are stained by the attachment of heavy metals. So what we get is we look at the heavy metals attached to the sample, not the biological material itself. And just because of that, we lose resolution and we have to be aware of possible artifacts. Now, the optics of an electron microscope, it's depicted here in this picture, is not very important. It's very analogous to the optics in a light microscope. You have a source, here's an electron source in a light microscope, it's a light source. You have a condenser lens, it focuses the beam on the specimen. You have an objective lens, and then we have finally an ocular projection lens. In the end, these electrons tend to be projected onto a screen, and we can snap a picture of that screen or we can detect using software what's on that screen. Now, another limitation in the electron microscope is that the sample has to be extremely thin itself, and this is because otherwise we get too much scattering. So we get a blurry image or no image if the sample is not very thin. When I speak about very thin, really think about much less than a micrometer, much less, so extremely thin. Now the sample doesn't have to be thin because of any problems with the depth of field. The depth of field in the electron microscope is very good. And when you see an EM picture, everything is in focus. That's typically the case, and it's always crisp. Okay, so how is the image formed? That is, I think, important that you understand what's going on. So let's just imagine here we have these arrows represent electrons that are focused on our specimen. And here's our specimen. And if we just have a piece of biological material, indicated here by my arrow, then all of the atoms in there are of low atomic number. Carbon, hydrogen, nitrogen, it's all low atomic number, even oxygen. So we do not have a lot of opportunity for these electrons to interact with this specimen. The interaction means they get scattered, and therefore they would not reach the objective lens and would not become part of the image. So effectively, organic material is transparent in the electron microscope. It's invisible, very poorly visible. So in order to get contrast, you have to add heavy metals, depicted here by my gray color on this darkened arrow. And so because of that, many electrons interact with the electrons that circle around, so to say, the heavy metal atoms attached to our specimen. They get scattered away and they don't reach the objective lens, and therefore we get a dark spot in the image, wherever that happens. So that's how the contrast in the transmission electron microscope is formed. So we're talking here about the transmission electron microscope. Okay, so if we understand this, then we can understand how we see things in the electron microscope. Now, the electrons that are formed at the source and that are focused on our specimen, on our sample, we call those the primary electrons. So let's say the light beam, in the analogy with the light microscope. The photons in the light beam and the electrons that come from the filament in the electron microscope, those are the primary electrons. They are focused on the sample. The ones that make it through the sample to the objective lens contribute to bright spots in the image. So the primary electrons that pass through the specimen form the image. Okay, So keep in mind, organic compounds are of low atomic number, are invisible, we need to stain. How are we doing?
Great.
All right. How would you like the Steve Miller Band?
Great.
I was the Steve Miller Band. This is the 60s or 70s. I had, when I was a student in high school, I had to listen, that was an exercise we had to do for English. We had to listen to this song and interpret the text and answer questions. It's a very old favorite of mine. It was more than 30 years ago. Training and listening, right? It's good. So, how can we stain samples and what kinds of images can we form in a transmission electron microscope? There are three main ways in which we can get contrast. The first one I call thin sections. The second one is negative staining, and then we have shadowing. Now, thin sections is an approach that really is analogous to bright field conventional microscopy. Conventional light microscopy. You just have a thin section of tissue. It's stained with heavy metals, we'll get to that, and that gives us an image. Such as here, we have, this looks like this is a section of muscle cell, and we see some actin and myosin. There's myosin here and actin. I need to stand right up. I saw myself in the video. It's scary. Now, mitochondria here. That looks like, I don't know, this might be something like a blood cell in a blood vessel, I don't know, that's in the tissue. But a lot of detail, right? And the image is very crisp. Okay, here we have a negative stain. Negative staining is used to view macromolecules or macromolecular complexes. This is a plant virus, I think. Like maybe a tobacco mosaic virus or a similar virus. Another approach is shadowing. This is a shadowed image. I think it's also a plant virus. And it's also used to look at macromolecular structures, but it can also be used in combination with another approach called freeze fracturing to look at very detailed structures of organelles and membranes. Okay, let's look at all of these in a little bit of detail, starting with the thin sections. So, what does it take to see something in the EM? We do not need to learn what's on this diagram. What you need to see here and appreciate is it takes a lot. There are many steps. So briefly, we have a sample, a piece of biological material, it could be a couple of cells that you have collected, or a piece of tissue. And that sample first has to be fixed. First of all, why? The electron microscope, because it works with electrons, has to work in a vacuum. The speeds are very high. If there's not a vacuum, that machine heats up. It heats up anyway. It heats up because the electrons collide with gases in there. You cannot have that. So to get a good image and to have a machine that works, the electron microscope, that tube where the sample ultimately is in a vacuum. And that means the cells have to be fixed, otherwise they would explode. So how can you fix? There are two ways of fixing. One is to add chemicals that cross-link proteins and macromolecules. Things like formaldehyde with aldehyde groups, or acetaldehyde, or glutaraldehyde. Those are cross-linking reagents, and they make networks between the macromolecules, and that keeps the overall structure intact. The problem is that as those chemicals infiltrate the sample, you might get a change in the morphology of your cells, so you might get some artifacts. So a better way is to freeze. And freezing is the best way to preserve biological material without any artifacts, as long as you can do it very rapidly. If you freeze a sample extremely rapidly, you prevent the formation of large ice crystals. Large ice crystals are a problem because they distort the shape of macromolecules and the shape of organelles in the cell. So you need to freeze very rapidly. So you fix by chemicals or by freezing, okay? And then you replace the water in the sample slowly with organic solvents, and ultimately you put in a resin that often under ultraviolet light forms a sort of a plastic. So you replace essentially all the water with an organic solution, and in that is a polymer-forming plastic structure. So that's what you get. And you sometimes, if you do certain types of fixation, you'll have to actually heat that in an oven. So imagine what heat does to a sample. It's not the best way, right? So the best preps are where you freeze rapidly and do all these replacements at very low temperatures under special conditions. That's expensive equipment. But in the end, you end up with a sample and it's in plastic, your cells are in there, you hope the structures are still intact. Now you have to slice it and make very thin slices. You use a special machine called a microtome. The best microtomes have knives that are made of diamonds. Diamond is the hardest material that you know, so you can get the best knife for the thinnest cut. You get a very thin cut to collect that strips of biological material on a thin grid of typically copper, and on that grid you do a final staining, and then that goes into the EM, and you look at it, it might look something like this. This is a mitochondrion here, and here we have some ER that surrounds it. The stain that we see here is heavy metals, things like osmium oxide is often used, and it binds to the lipid bilayers that make the membrane. So that's how we see the ER, and here the outer membrane of the mitochondrion, and we see the cristae here, which is all the folds of the inner membrane of our mitochondrion. A lot of detail we can see. So that's a thin section. Now, as a follow-up on a thin section, we can do another technique which we can combine. After we've sliced our samples here, we can come with an antibody that has been bound to gold particles. And what that allows us, it allows us to see specific molecules. So what we can do is, if we have an antibody to a specific protein, say catalase, a protein found in peroxisomes. There's our antibody. We have the antibody bound to another protein, protein A. It's a protein of bacterial origin, and it binds to this general part of antibodies. And we have that protein A attached to a gold particle, a sphere of a very defined diameter. So if we wash this over our thin section, wherever we have catalase, the antibody will bind, and the gold particle will be there at some distance. So then if we put that in EM, we can see here, I think here it's, I'm going to put you in the dark slightly, okay? You can see better. Over here we can see some of these circles, which are the gold particles staining the catalase in the peroxisomes. You can see them in here as well. Can you see them? Can you see or not? Seeing is believing. You don't have to believe me. Okay, so we can using this method, we can see where the catalase protein is. We see other structures here, mitochondria, this is maybe some ER, I'm not sure. The membranes often pick up these heavy metal stains, especially osmium tetroxide is something that's easily attaching to membranes. So we have the immunogold labeling, as we call it, to look at the location of the specific molecule, and then the background, all the membranes are stained with a heavy metal. The heavy metals also bind to proteins and ribosomes, so we see some grainy material in here. And we also see a lot of dark stuff here in the peroxisomes. Maybe that's actually the iron-containing catalase itself that gives us some contrast there. Okay, so immunogold labeling is a method to combine these thin sections It's used for looking in high resolution where structures, specific molecules are within cells. Keep in mind that actually the size of the antibody is such that we cannot really see exactly the location of the catalase. So say if there would be a protein on the membrane, then actually the size of the antibody is larger, and that's with the gold particle attached especially, larger than the thickness of the membrane. So you could not really use this method to see if a protein fits on one or the other side of the membrane. Just don't have that resolution because of the size of this structure. Okay, time for more light presentation notes. Okay, the next way to make contact is negative staining. And negative staining is a method that I like to equate to this ancient painting technique that some of our ancestors used in France 50,000 years ago. Have you heard of the caves of Lascaux? If you've read Jane Austen books, you know, the Mammoth Hunters and things like that, that's about those people. Anyway, they were making paintings in their caves. They were cavemen. And what they were doing is they would say, put a hand on the surface, and they had a pigment, a colored earth in mud in their mouth, and they would spit at it. And so you'd get a color around the area where the hand is, and you take away the hand, and then you have that image. So that's what we see here. That's the image of a hand. And that is effectively a negative stain. And this is essentially the same method that is used in EM. So let's say we have a macromolecule or a structure composed of macromolecules, proteins together, and we have that on a very thin grid. We have it isolated, a thin layer of carbon, a very thin film of carbon just as a support. And that film of carbon then sits on the top of our copper grid, which can go in the EM. So before we go in the EM, what we do is we add a solution of heavy metals, just a salt solution. And we just let the water evaporate, and so the salts stick to the grid below, to the carbon surface, but whenever there's organic material, the heavy metal salt cannot be deposited there, because that organic material is in the way. So we put that in the electron microscope, and if we put the primary electrons on our specimen, the primary electrons are blocked where the heavy metal salt is accumulating around the organic molecules, but where the organic molecules are themselves, it's more transparent, so you get brighter spots because those electrons pass through. So what you get is bright sections in a dark background. That's a negative stain. So here we have an image. These are microtubules, isolated from cells, and they're put on a grid, on a thin carbon film. A heavy metal salt is deposited. That salt actually tends to accumulate a little bit around the edges of our macromolecules. So you see that dark outline very close to our microtubules. And microtubules are hollow. Some salts actually make it in. And the resulting image is this negative stain. You really get the sense that this is a tube-like structure. All right, and this is just 100 nanometers here, the scale bar. So you see we're really looking at resolution in the, say, 10 to 5 nanometer range, which is pretty low. Okay, the next method is shadowing. What do you do in shadowing? In shadowing, we have our specimen, and we put it in a chamber, and the specimen has to be fixed, and it can be done in one of two ways. Either we keep it very cold, or it cannot be fixed. So then we have a vacuum in our chamber, and we have a source here of heavy metals. Platinum is often used. This is just heated, and what happens is that platinum atoms jump off from that piece of wire, and they start to rain down in this chamber. We get the deposition of platinum atoms all over the place. But since our wire here is not straight above our specimen, but it's a little bit to the side, we get the platinum down on our sample under an angle. So if we look here and blow up where our specimen is, in gray here is depicted where the platinum would come down. But when there's an object there, an organic molecule or a structure we're interested in, then we actually get a side where there is no platinum deposition, a shadow. Okay, so what we do is we deposit the heavy metal from an angle, and you need to get this into the EM later. So what you have to do is you have to keep that shadow image together. And to do that, you add a thin layer of carbon, and that carbon comes also from a source that's heated, but we rain it down, so to say, straight from the top. Everything gets covered. The carbon just serves as a glue. So then we can remove the organic material, and we are stuck with a replica, which is a shadowing image, and we view that directly in the transmission EM. And I like to say that these samples appear as if you have a landscape where you might be flying over, and it has been snowing from an angle, but the snow is black. So let's have a look at one of those images. Here we have an image. So this is a macromolecule. It might be actin filament. I don't remember. It's not that important. So where in the shadowing source, where was the shadowing from? Was it from the left, from the right? If you look at your perspective here, look at this image. What do you think? Yeah, it seems like it's from the right, right? So we have, here is the shadowing source. Dark material deposits on this side. This is a macromolecule on the grid, or a macromolecular structure on the grid. So there's a shadow side here where we don't get that material. Now I lose my thinking. You can see in the background here also, this is just grains and particles that are just part of the background. Okay, so I think it's good to understand this method. And now we can go further and we can use the shadowing approach to also look at membrane structures. Now I've told you in the transmission EM, if we do thin sections, we can stain for membranes. But we have to remember that the fixation often can change the appearance of our real sample. So even though we look at high resolution, we're looking at a sample that's not so well preserved. It's somewhat like if Martians would come down, and if they would find mummies that the Egyptians made, and if they take the appearance of those mummies for the appearance of real humans. And obviously, they would be a little bit off. Okay? Because that's not exactly what we look like. It's close, and we're not cats, that's clear, but we don't look like the mummies also. That's chemical fixation. So a better fixation is if you can really rapidly freeze and do nothing to the sample, nothing else. And that's what we do with freeze fracture. So here what you do is you very rapidly freeze, and you get a very small biological sample, because that freezes rapidly. And then you take a very tiny hammer or knife and you hit it so that it breaks. Now, we have to remember that most of biological material is water. And between water atoms, or sorry, water molecules, there are hydrogen bonds. There are many of those. The hydrogen bonding network between water molecules is strong. Therefore, breaking right through the ice is not energetically favored. But if we encounter a biological membrane, the two lipid bilayers, or sorry, the two lipid layers that form the bilayer are deeply connected. So we would preferentially get breakage between the two planes of a membrane. This is indicated here in this diagram. So if these orange sections here are, say, cytosol of a cell, and what's in blue there is a membrane, a lipid bilayer, then we would get preferential breakage between the two lipid bilayers. But importantly, we completely preserve the geometric shape of this membrane surface here. So we break between the two bilayers, and the proteins go in one or the other monolayer. We break here right in between. So then we have this breaking surface, and we can remove extra water. That's called etching. This is done by just increasing the temperature. All of this is done at a deep freezing temperature. But if you slightly increase the temperature and apply a very low pressure, then some of the water will just evaporate, sublimate, actually. Not melt, but just go straight from solid into the gas phase. That's called etching. You can do that. And then you shadow. So you deposit platinum under an angle, and you make a carbon glue go over the top. You remove the organic material with a weak acid, and the replica goes into the EM, and this is what you see. The image is extremely crisp. And we really believe that there is some curvature here in the membrane that we can see. These are parts of nuclei, and what you can see here is, for instance, a nuclear pore structure. Proteins that form a pore by which mRNA can move out of the nucleus and proteins can get in. So here we're probably in the water, it looks like, with some grainy proteins in there. And here we have maybe some other membrane surface, I'm not sure what it would be. So once again, a question we could ask is, if we look at this image here, where would the shadowing source have been if we look at this image? Try to understand how it's formed. So you look at where it's darker,